Record. All right. First of all, I just want to say happy birthday, Shakira. And Punxsutawney Phil saw a shadow this morning. So 2 more months of winter. 6 more weeks. Yeah, 2.5 months. All right. Well, but apparently we're gonna have like a winter storm coming again. And if that happens, good thing we have the video. Okay. We're starting the second half of the House of Calculus. Ready? We're starting the second house of the. Sorry, let me slow down. The second half. Here's the derivative with respect to x, and we've already kind of got this one pretty much built. There's still some rooms in there that need some painting, some touch-ups, and we'll come back. But now we're ready to start building the second half of the House of Calculus, which is going to be awesome. It's going to be even better, right? Because now we're more skilled in our construction techniques. And then we'll build this little shed off to the side at the very end. Okay, so we can keep our math tools in there. But the second half is integration. Okay, and they complement each other nicely. In fact, the fundamental theorem of calculus that we'll learn here in this chapter relates how derivatives and integrals are related to each other. So the first thing we're going to start with on 4.1 is we're going to learn how to find an antiderivative. Okay, so antiderivatives just means undifferentiating, underivativating, differentiating. We're going to be undoing what we did. Okay, now when we anti-differentiate is what it's going to be called, we're actually finding something called an indefinite integral. And so these two things are going to become synonymous. If you're asked to find an antiderivative, it's pretty much the same as finding an integral. Okay, an integral. Antiderivatives and integrals are really the same thing. Okay, now there's two types of integrals. There's a definite and indefinite. So right now we're just going to learn the indefinite integral and learn why it's indefinite. So let's say that we have this function capital F, big F, if you will, right? Big capital F, whose derivative is defined as such. The derivative of big F prime is now little f, and it equals x squared. Can anyone tell me what the function big F was before we took the derivative of it? In other words, what did I actually take the derivative of to get x squared? 1/3 of x cubed. Good. Yeah. So we know it has to be a 3, right? Because the power rule says when we differentiate, we subtract 1 from the degree. So it had to be a 3. Now, if you want to do guess, check, revise, it's a really good method. Guess, check, revise. We're going backwards. So most people just start off with an x cubed guess. Braden nailed it on the first try. So if that's your guess, when you check it, big F would be 3x squared. And now you're like, well, holy crap, there's an unwanted 3 there. I got the x squared part, but there's an unwanted 3. No problem. Let's go back and correct ourselves and put something in front of the x cubed that will neutralize the unwanted 3 that's being multiplied. Well, how do we neutralize an unwanted 3? We put its reciprocal there. Yeah, 1/3. This is what I call pretty much a correction. Okay. It's really going to be part of what's known as the power rule for integration or anti-differentiation, but it's a correction, right? We have an unwanted 3, so we put this correction of its reciprocal. It's kind of like when you're eating a plate of enchiladas and you get heartburn, the 1/3 would be kind of like the antacid, right? They neutralize each other. So this right here is called an antiderivative of little f of x. That's an indefinite article, an antiderivative, not the antiderivative. Why? Oh yeah, very good. So we have 1/3 x cubed and plus 100, right? Is that another one? Well, let's see. If we took the derivative of that, we get 3 times a third. 3 times a third is 1, x squared, boom, plus the derivative of 100 is 0. Yeah, so 100 is not really special in this case. 100 is just an arbitrary constant that when we take the derivative, we lose information. We lose the constant. So what we do is we make an allowance for there being a possible constant. So I would say big F of X is 1/3 X cubed plus, and we typically, I mean, you can be kind of cavalier if you want, but we typically write capital letter C for constant. If you deviate from that, then it's up to you, right? So there's all kinds of memes out there for like plus C, plus C. Don't forget plus C, right? Because students want to forget plus C, plus a constant. But don't forget plus C, okay? Now, could you put plus capital D there? Sure. Could you put the C in the front because it's commutative? Sure. But we typically put it at the back. All right. So this is called the general antiderivative because it has the plus C in it. Okay. Plus C. Now, if we wanted to find C, like if we wanted to know, hey, did that original function actually have a C value other than 0? Then we would have to know something about the function. Okay. To find C, we need what's called an initial condition. Which is basically a point on the graph of big F. Okay. If I have an ordered pair, if I had one point that I knew that original graph passed through, I could plug in an A for X, a B for F of X, and solve for C. Okay. So when we have that, that's going to be called a particular solution. And I'll just label that down below. Now let's think graphically what this is going to do. We know the graph of 1/3 X cubed is our X cubed parent function. The 1/3 is a vertical compression. But what would a plus C value do from one graph to the next? Plus 5, plus 10, plus 8, shift it up or down, right? So if you look right here, I kind of have what's called a particular solution. These are called particular solutions instead of general solutions. So let me see if I can spell it. Solution. There we go. So this would be a particular solution. These are all equal signs here. I know the image is bad, or maybe they're not equal signs. They're arrows. Okay. That graph goes with that, this one with that, so on and so forth. All right. So this would be very particular because it's the only function in the whole wide world whose derivative is x squared that happens to pass to the point 0, -2. It's the only one out there. Very particular, right? But that's different from the one above. So if we know any point, it could be any point on the graph, we can find the particular solution. And you can clearly see graphically that these are all just vertical shifts of each other. Now that's going to tie in later to what Landon and Devin are going to teach next Tuesday. Next Tuesday, if you want to mark your calendar during 7th period, Devin and Landon are going to teach what's called slope fields. And it's going to look something like these pictures here. It's a way to generate that picture without finding an antiderivative, without actually going backwards like we did. It's a pretty cool thing, but intriguing. Yes. Mark your calendars next Tuesday. Okay, so let's try this out. Example 1, we're going to find the general antiderivative. General means, again, plus C for each of the following using your knowledge of how to find derivatives. If you don't have your derivatives memorized, going backwards is going to be impossible, right? Impossible, really. Okay, now we're going to practice 2 things here. We're going to practice not only the expressions, finding what their antiderivative is, but we're going to practice the notation as well, okay? So on part A, we have little f of x equals 2x. I want to find the antiderivative. That is, I want to find the function that came before it. So when we start with little f, there's really nowhere to go notation-wise when we go backwards other than to make it a capital letter, okay? So that's why we use a capital letter as opposed to a lowercase. So that's the left side's antiderivative. And now the right side, what's the antiderivative of 2x? X squared. Good. And then we put a plus C. And you can check. The nice thing about going backwards here is because we know how to take the derivative and we know what the derivative should be, 2x, you can always check your work. It takes a little bit of discipline, but you can guess, check, and go back and revise it. What's the derivative of x squared? 2x. That's what I got above. What's the derivative of a constant C? 0. Boom. We awesome. We awesome. Okay. All right. Now let me show you another way to do this. Okay, because x squared plus c is intuitive. And this is going to kind of pave the way for 4.4. I'm going to say that the 2 is a constant multiple. I'm not going to mess with him. He's right there. Okay. I'm just going to leave him in my answer. Like, you go ahead and line up in the answer. I'll meet you there shortly. Okay. And now I'm going to come over here to the x. I'm going to be like, what was there before? What was there before? Well, if it's a 1 now, it had to have been a 2 before, right? And then I'm going to focus on the x squared by itself. If I take the derivative, I get 2x to the first. And I'm like, dang, I have that unwanted 2 again. So now I'm going to come back in here. And on this piece alone, I'm going to make that correction of 1/2. Okay. And this 2 over here, that's just kind of standing in place saying, what are you doing over there? I end up calling him the writer. And then, of course, we put plus c. Now, you don't need to do it like this right now, but this is gonna be helpful later on. Now, when you simplify that, what is 2 times 1/2? It's 1. So we end up with x squared plus c. All right. You're going to have one more type of a number that might actually be in front of some of your antiderivatives besides a rider, which is a constant multiple that's there in the beginning. It'll be there in the end. A correction of a constant multiple by its reciprocal neutralizes the acid. And then you'll have one other one that comes from a rule. Okay. But we'll talk about that later. All right. Letter B. We got little f prime now equals x. Now, when you see a prime there and we're going backwards, all you got to do is remove one of the primes, right? So the antiderivative of little f prime is just little f. And what's the antiderivative of little x? 1/2 x squared. Boom. And now to make it a general instead of a particular solution, plus c. Yeah, if you ever leave off the plus c, we're going to assume you're putting a particular solution down that has c equals 0. Okay. There you go. Now that's still pretty intuitive, right? There's something to this though. Watch. We ended up with up here we had an x squared and it ended up 1/3 x cubed. Here we had an x to the first, it ended up 1/2 x squared. There's something to that. Now look at this one here. Letter C. Left side first. What would be the antiderivative of big F prime? Big F. If it has a prime there, you just take one away. Another name for big F prime is little f. Okay. Now you got 2/3 x to the 4/7. This one is not quite as intuitive as the ones we just did, right? Ugh. So here's what we could do. We can use that little trick that I just taught you. 2/3 is a constant multiple. He's there in the beginning, he's there in the end, right? Just like when we take the derivative, like the derivative of 5 sine of x, the 5 goes along for the ride. It's just 5 times the derivative of sine, which is cosine. Same thing when you're going backwards. If you have a constant multiple, leave them there, leave a little space, and then do what you know to do here. If we have a 4/7 in the derivative, we know then that before we took the derivative, it had to be 1 degree. It had to be bigger, right? Because when we do the power rule, by taking the derivative, we subtract 1. So I know it had to be 1 value larger. Well, what's 4/7 plus 1? That's 4/7 plus 7/7, which is 11/7. Now, this could be your guess. I'll just put a G for guess. That could be your guess. Now, your check. When you check, what's going to happen? The 2/3 is still there. And when you check, you get 11/7 times x to the 4/7. And now you revise it because you're like, crap, I have an unwanted 11/7. How do I get rid of an unwanted 11/7? 7/11. There you go. You multiply by its reciprocal. That's the correction. Guess, check, revise. And all this stuff that I did here is on my workbench, really. But I don't want it to interrupt the flow of the problem, so I'll just put it over here for now. And now I know it's going to work, so now I just put plus c. And technically we're done. But here's what we could do now. We can simplify. 7/11 times 2/3 is 14/33 x to the 11/7. Yeah. So notice what we've been doing so far. Let's review this real quick. We had an x squared, and it became 1/3 x cubed. We had an x to the first, and it became 1/2 x squared. We just had a x to the 4/7, and it became 7/11 x to the 11/7. Do y'all see a pattern there? What is it, Ethan?
It's the numerator and the denominator switch.
The numerator and denominator are switched? What do you mean by that?
The exponent and
The coefficient? Yeah. They're, well, not switched. What's a better word for it mathematically? Not inverses, they're reciprocals. Yeah, they're reciprocals. You have a 1/3 and a 3, you have a 1/2 and a 2, and you have a 7/11 and 11/7. Okay. That actually happens every time when you have an exponent that's a number, when it's a power of x. Okay. And so that actually becomes a rule rather than a correction. It's called the power rule for anti-differentiation. Let me give it to you right now. It says if you have big F prime of x of the form a times x to the n. Okay, that's very similar to what the power rule for derivatives had to look like, right? Here's what it's going to be. Let your a just stand fast. He goes along for the ride. Leave a little space. Add 1 first to your exponent to get your new exponent, and then multiply by the reciprocal of the new exponent. I'm sorry, that should be f at that point, not f prime. And that's it. And then you just tidy it up with the plus c. All right. So remember when we took the derivative, we multiplied and then subtracted. Yes. Let's review the derivative. The derivative with respect to x of a x to the n was a times n, and then times x to the n minus first. So we multiplied and then we subtracted. Well, if an antiderivative is truly untaking the derivative, if you want to undo something, you know that you have to do the inverse operation in the reverse order, right? So instead of multiplying and subtracted, what we're doing here is we're adding, then we're essentially dividing. Okay, when you multiply by 1 over n plus 1, it's like dividing by n plus 1. But the reason I don't like to say dividing by, I'd rather put the reciprocal in front for the cases when we have fractions. Okay, like 4/7 and 7/4. Okay, so that is going to be known as the power rule. Power rule for, I'm just going to write this shorter word, integration. The power rule for integration, which is also known as AKA anti-differentiation. Anti-differentiation. Yeah. Okay. Derivative is multiply and subtract. So going backwards, add first, then divide, or multiply by the reciprocal. And then the constant just goes along for the right. And then once you have everything in front, you can combine the coefficients. Okay. So let's see then if we can implement that here. G prime of x. Well, if I can write it in the form ax to the n, then I can use the power rule, right? So just like if I were taking the derivative, my first step would be to rewrite it as 1 times x to the negative second, or just x to the negative second. And now I think we're ready to go. So here we are. On the left side, we just get little g of x, remove the prime. The writer in this case is the 1. There's just a 1 there. So leave a little space. We add and then we divide. We add first. So -2 plus 1 is -1. And then you either divide by -1 or multiply by the reciprocal of -1. I'll just keep that same format going. Plus c. Add to get your new exponent and then multiply by the reciprocal of the new exponent. And then put plus c. And of course, when you clean that up, that's the same as -1 over x plus c. And here's again the best part. If you're not sure if that's correct, what can you do? Take the derivative. You should get 1 over x squared. Wow. Oh, it's almost hard to go wrong when you're taking the antiderivative if you have the spirit, the sisu, to guess, check, revise. guess, check, revise, and repeat, right? Yeah. Yeah. Like when you're washing your hair, sometimes you don't know when to stop because the instructions say to wet, lather, rinse, repeat, right? And then you get stuck in this endless loop in the shower. And then you get out of shampoo and the hot water's gone. You're like, damn you, Heads and Shoulders, whatever. Selsun Blue, I don't know what you'll use. Denorex. Well, that's like a medicated shampoo for severe dandruff. Let's try this one. dy dx equals cosine of x. Well, what does the left side become in Leibniz notation? It's just y. Yeah. And now this is cosine to the first, right? So this must be cosine of x to the second times 1/2. Boom, I'm done. Plus c. Thank you very much. I was just born this way. I can't help it.
You sound like you're going to supposed to be healthcare.
Oh, is that right? No, because cosine of x is not in the form ax to the n. And if you try to, let's try it. Let's check. Let's check it, right? The left side is dy dx. Yeah, that's what I was talking about. I got the left side, right? I got the page numbers already written for my new book. 2 times 1/2 is 1 times cosine of x to the first. So we get cosine of x to the first times the chain rule, negative sine of x. Ay, caramba. My original function didn't have a negative sign in it. So yeah, the power rule doesn't always work, does it? No. Okay. It only works if you can write it in the form ax to the n, just like it didn't always work for derivatives. So now we just have to rely on this. What do we take the derivative of to get cosine? Sine. And then plus c. Yeah. And then you can check. What's the derivative of sine? Cosine. Way to go, me. Way to go, me. All right. Everyone good with that? Now, here's the good news. The power rule for integration is the only rule of integration you'll have. It's the only rule. Yeah. Everything else requires a little bit of ingenuity and finesse and memorization and recognizing patterns, right? Which is why it's the most fun thing we could do in here. Yeah. Going backwards. Yeah. All right. So here's a table. Here's a table of antiderivative formulas. And really all they are is I took the table for derivatives and I flipped the columns around. Okay. So if you have a function c times f of c, where c is a constant, the antiderivative is going to be c big F of x plus big C. This is what I call the rider. He's just riding through the problem. He's like, you have a truck and he's in the back of the truck. He's like, hey, can we go somewhere? Yep. Can I ride in the front? Nope. Get in the back of the truck. And then you go about your business and then you get home and he's still there. And you're like, you still here? And he's like, yep, just been going along for the ride. Right? He's there in the beginning, he's there in the end. Plus C. All right. We can do this. This was nice. If we have multiple terms, just like we can take the derivative of it, term, boom, boom, boom down the line, we could divide and conquer as well if they're terms, added or subtracted. So the antiderivative of little f plus or minus little g is going to be big F plus or minus big G, plus a constant, of course, plus C. Here's the power rule, right? You can even augment it. Put a little a in front because there could be something there. Ax to the n, where n is not equal to -1. A goes along for the ride times add 1 and then multiply by the reciprocal. Add first and then multiply by the reciprocal second. Now, notice it says when n is not equal to -1. You can't tell me what to do. Table of antiderivative formulas. I'm going to try it. X equals negative. That's right. I'm going to call this one G double prime. Okay. If G double prime is x to the negative first, then what would be the antiderivative of the left side? G prime, right? Whatever it is, if you're going backwards, you just take 1 prime away if there's some there. And now I'm going to use the power rule. Everybody get ready. I'm going to use the power rule. Leave a little space. -1 plus 1 is what? 0. And now I'm either going to divide by 0, or as Mr. Corpiello said, multiply by the reciprocal of 0, which is 1 over 0. And then, of course, plus C, because I'm no fool. No siree. I'm going to live to be 103. I play it safe for you and me because I'm no fool. Is that right? No, it's not. Because multiplying by 1 over 0 is multiplying by plus or minus infinity. It's the same as dividing by 0. Can we divide by 0? No. So crapiola. I guess you're right, stupid table. You were warning me, not just telling me I couldn't do it because you're arbitrarily mean. I guess it can't be done. So I guess that's the only one that we can't anti-differentiate, right? If you have g double prime equals x to the negative first, I guess there's just no known antiderivative, is there? Unless we think about x to the negative first as also being 1 over x. In which case, we know that going backwards now, finding an antiderivative, Hank, is simply just asking yourself, what do I take the derivative of to get 1 over x? And I'm like, oh, I remember. The what? The natural log of x. And then, of course, plus c. I'm no fool, no siree. Now, here's the thing. We always have to try to preserve as much of the original domain as possible. When we start with 1 over x, x can be positive or negative, can't it? Except 0. If I use the natural log of x as the antiderivative, now I'm hamstringing myself because now I can only use positive x's. See that? I can only take logs of positives. What can I do to the natural log of x to accommodate negative values like in the original function? Absolute values. That one. Field goal, right? Well, guess what? That's what it is. If you ever have 1 over x, which is also known as x to the negative first, that's the only time the power rule will fail when it's written in that form. The only time. And then who comes to the rescue in that one case? Natural log. But it's the natural log of the absolute value of x plus c. Okay? And we know when we test it, going backwards, the absolute values go away, right? We take the derivative of the natural log. All right. So natural log, you're my hero. All right, here we go. Don't think too hard. What's the antiderivative of e to the x? E to the x plus c. Very good. If you're your own grandpa, you're also your own grandson. Duh. Right? I like to go fishing with my grandpa. I go by myself. Right? Very good. Hey, cosine. What's the antiderivative of cosine? Sine plus c. Don't forget plus c. What's the antiderivative of sine? Oh, negative cosine. Sneaky, sneaky, right? If you were just to guess cosine, you would check and say, the derivative of cosine, because it starts with a co, is negative sine. But I wanted a positive sign. So how do you neutralize an unwanted negative 1 factor? You add another negative 1 factor, which is like dividing by negative 1. So you got, that's why guess, check, revise is so good. Plus c. All right. What's the antiderivative of secant squared? Are you looking or guessing or tan plus c? Good. Yeah, it's tangent because the derivative of tangent is secant squared plus c, of course. Good. All right, new column. Cosecant squared. What's the antiderivative of cosecant squared? Is it cotangent plus c or negative cotangent? Not probably. It's better than experimental probability. It is theoretical probability, probably, yes, right? Negative. Secant tangent has an antiderivative of what? Secant. And it's simply because the derivative of secant is secant tangent plus c. Cosecant cotangent. Negative cosecant. The negative is the neutralizer. Because if it has a co, it has a negative derivative. What is the antiderivative of 1 over the square root of 1 minus x squared? Inverse sine. Inverse sine of x plus c. Good. Or arc sine, either one, right? Yeah. This one looks intimidating. But then not if you recognize it. It's like, what's up, arc sine's derivative? Yep. Shoddy in the club. Hey, look, here's another shoddy in the club. 1 over 1 plus x squared. What's the antiderivative of that? Inverse tangent or arc tangent plus c. Plus c. Oh, look at this rascally rabbit. The absolute value is gone, so we have a larger domain, but it's function minus number. This one is arc secant. It doesn't show up that often. Now, here's the thing. Because x in the bottom at this point could be positive or negative, I preserve that, and arc secant has an absolute value on it as well for domain purposes. This one right here, if your brain is full, you can kind of put that on the waiting list. Kind of like Hank when he flew with his dad all last week.
Yes,
Right.
waiting list.
Yeah. Oh, you probably did. You weren't on the waiting list, right? You just sat in his lap while he was flying. Yeah.
No, I was on
And,
waiting list.
and he made airplane sounds for you while you were in the air.
He went-
Yeah. Yeah. All right. Example 2. Here we go. Find all the functions in the whole wide world G, little g, such that little g prime is 4 sine of x plus all of that minus all of that. Okay, so we need to clean up the garbage, right? We have to make this look like something we either recognize or can write in the form ax to the nth power. So here we go. Let's clean it up from left to right. G prime of x is. The first term is 4 sine of x. I think I know what the antiderivative of that is, but I'm not going to take the antiderivative of any of the terms until I'm ready to take the antiderivative of all of the terms, because the notational burden is too great. Now, here's the strategy. This is a quotient of 2 variable functions. There is no quotient rule for anti-differentiation like there is for derivatives. So what we have to do is do something clever. And one of the clever strategies that we're going to have is we can split up numerators, okay? By putting each term in the top over the entire denominator. So let's see what that becomes. That becomes plus 2x to the 4th over x minus x to the 1/2 over x. Notice I wrote it as a rational exponent plus x over x. This is actually what we did early on when we were taking derivatives as well. When all we knew was the power rule, we had to make everything look like that form. Now, the next one, we got to be a little bit more careful because there's a negative as well, and we also have to split it up. So that's a negative, let's see, a negative 7x cosecant squared of x over x, and then minus, when I distribute, 1 over x. All right, now the good news is I took 3 terms where the last 2 were kind of ugly, and I split it up into 3, 5, 6 terms. But I'm not quite ready yet. So working straight down, let's clean up now. First term, still ready to go. Thank you, first term, for being here on time, being ready to go. This one is now 2x cubed. Oh, that's looking promising, isn't it? Minus, we subtract these exponents, 1/2 minus 1, negative 1/2. And look at this one, x divided by x, that's 1. Yahoo! And now in the last 2, those x's divide out. Cheese and rice, this is looking better. Now, minus the last one, it's 1 over x. Do you want to leave it as 1 over x or write it as x to the negative first? I'm going to leave it as 1 over x because we're smart. Yeah, I'm already going to realize that if I wrote it as x to the negative first, I'm going to end up dividing by 0, and I have to put out the natural log signal for the natural log to come save me, like Batman. Okay. All right, let's go for it. Now we're ready to go. What becomes of the all-important left side? What's the antiderivative of little g prime? Little g. All right. And then 4 sine of x. Well, look, 4 goes along for the ride. Constant multiples go along for the ride. What's the antiderivative of sine? Negative cosine. And again, if you're not sure, put cosine and then quickly check in your head. If you took the derivative of 4 cosine, you would get negative 4 sine. And when you compare that to up above, you have to get a positive 4 sine. So how can you neutralize the unwanted acid? Put a negative 1 there. That's the reciprocal of negative 1, right? Negative 1 is just unique because it is its own reciprocal. But normally we put the reciprocal of the unwanted number, okay? All right, that's cool. Next term, 2x cubed. Well, look at this. I'm not going to bother with making 2 something like 4. I'm just going to say, hey, 2, you're going along for the ride. Boom, 2. Leave a little space now and say, okay, x cubed, you're going first. What are we doing first to x cubed? We're going to add 1 to get 4, and then we're going to multiply by its reciprocal. Boom. And then when we come back, we'll combine the exponents. It is plus 2. Sorry. Dang, nice. Thank you. Thank you. No, I didn't miss anything. Y'all got it. I did miss something. Sorry. And now the next one, this next one is minus to start with. Leave a little space. It's in the form x to the n. We add one first. Negative 1/2 plus 1 is what? It's 1/2, right? Negative 1/2 plus a full 1 is positive 1/2 times the reciprocal of the new exponent, which is 2 or 2 over 1. Awesome. Next term, we have a 1. What is the antiderivative of 1? X. Good. If it's a constant, all you got to do is add an x to it because the derivative of x is 1. Right? If it were 5, the antiderivative of 5 is 5x. Are we okay? All right. So those all take care of the power rule. Constants, you add an x. Now, the next one, you got -7. Cosecant goes along, or -7 goes along for right. What's the antiderivative of cosecant squared? Negative cotangent. So that negative cotangent is going to make this a plus cotangent of x. And then before you leave that term, check and revise. Okay. What would be the derivative of cotangent? Negative cosecant squared. And then the 7 becomes negative and it's boom. And then, of course, minus over here, we don't have to do the whole save me natural log. We just invite them to the party to begin with. It's the natural log of what? Absolute value of x. And then what? Plus c. Okay. You can wait to put plus c until the very end. Now, it's interesting to think, if you technically thought of each term as its own problem, shouldn't they each all get their own plus c? Plus c sub 1, plus c sub 2, plus c sub 3? They would all just add up in the end to one gigantic new and improved unknown c. Yeah. So you can save it to the end. All right, now all we have to do is pretty it up at the very end, all the same color, -4 cosine of x, and then 2 times the fourth. Oh, that's just a half. Okay. -2 square root of x, that looks good, plus x, plus 7 cotangent of x, minus the natural log of the absolute value of x plus c. Boom, there it is. It's not only fun, it's easy. It's been easy. Yeah. Guess, check, revise. Sisu, guess, check, revise. Sisu. Help yourself, help yourself. It doesn't take long. You got an unlimited supply of mathematical workbench space. Yeah. Okay. Comments, questions on that? Will you ever see one that ridiculously long and cumbersome? Probably not. Maybe. But if you can do that one, you can do the easier ones, right? Okay. So far we have mathematical synonyms. We have an antiderivative. An antiderivative is the same as what's going to be known as an indefinite integral. There's notation for that I'll teach you in the next section. But an antiderivative and an indefinite integral are the same. And now they're going to also equal a solution to a differential equation. They all three mean the exact same thing. The only difference is how it's presented to you. It might ask you to solve a differential equation. It might ask you to find the antiderivative, and there's actually some notation for the indefinite integral. That's that super long elongated s with the dx behind it. That is going to become like the ddx. It's going to imply that you find the antiderivative of what follows. Okay, like ddx implies to find the derivative of what follows. So a solution to a differential equation. Let's define what it means then to have a differential equation. A differential equation is simply an equation that has a derivative in it. That's it. You see an f prime or an f double prime or something, and there's an equal sign in it, that's a differential equation. Now, solving differential equations is a little bit different than solving like conditional equations, like finding the values of x that make it work. Solving a differential equation, it means getting back to the original function, okay, from which it came. So if it's like y prime, you want to get back to y. If it's y double prime, you want to get back to y. You would just have to do it twice in succession, okay? When you find the antiderivative and you put the plus c, that's the general solution. But sometimes it'll ask you to find the particular solution, and that's when you need the initial condition to plug in to find the value of c. That's called the particular solution, like the individual graphs that we saw up above that pass through a particular point. All right. Now here's the thing. You always find the general solution first before finding the particular. That's the sequence. You can't go straight to the particular. So if it asks you for just the particular, you have to know to find the general solution first. Sometimes it might ask you to find the general solution on one part, and on the next part, it'll say, oh, now using this point, find the particular solution to the one above, okay? The method for solving the general solution or finding the general solution is, of course, anti-differentiating, going backwards. So let's look at example 3. Solve the differential equation. F prime equals 3x squared plus 1 if f of 2 is -3. Okay, all right. First of all, it says solve the differential equation. I have a derivative and I have an equal sign. So it is a differential equation. That's good. Solving it means getting back to the original function, which in this case is getting back to what? If it's f prime, we get back to little f, okay? So that's what I want to get back to, little f of x equals. That's what I want. If f of 2 is -3, what do you think that is? That's a point. On the original function f that we're trying to find, it passes through the point 2, -3. This is your initial condition. Now, initial in this case doesn't mean corresponding with x equals 0, right? That's a little bit different. Initial condition can be any ordered pair that satisfies the general solution, okay? So here we go. Do we need to do any rewriting on the right-hand side of f prime? No, it looks like a crunch wrap supreme to me, right? Good to go. So what happens on the left side? The antiderivative of little f prime is? On the left side? Little f of x, yeah. Don't take that for granted. Your notation will always lose points if it's lacking. And now 3x squared becomes what when you anti-differentiate? X to the third. Now, you have a couple of options there. You could just say, oh, well, that 3 just goes right back up there, right? Or you could do it like I just taught you, right? 3, you go along for the ride. You stay, get in the back of the truck, don't move. And now I add 1 to get 3, and I multiply by its reciprocal, boom. And then, of course, when you combine those in the end, you get 1. So I don't care if it happens to be the perfect coefficient, if you show it like I did in the lavender, or you just say, oh, I'm lucky, the 3 goes right back up. It doesn't matter. What matters is the derivative of x cubed is 3x squared. That's what matters. And then plus the antiderivative of 1 is what? X, right? Not 0. We're going backwards. So the antiderivative of 1 is x because the derivative of x is 1. Whew. Are we done with the antiderivative? Is that, oh, plus c. Yeah, don't become a meme. Don't be a meme yourself. Remember plus c. Yeah. All right. This is the general solution. General solution. Done. Now, we're going to use the ordered pair to find the value of c. Here's what we do. We say at the point 2, -3, colon. Again, we always indicate when we plug in a point somehow. Or you could say for f, or I'll say here, or for f of 2 equaling -3, colon. That's just a little bit fancier. You're going to plug in now. So we're going to get -3 for f of x equals 2 cubed plus 2 plus c. So -3 equals 8 plus 2, which is 10. And we solve and we get c equals -13. And now, guess what we have to do? Plug it back in. We don't stop there. So a good transitional word. So f of x is x cubed plus x minus 13. This is the particular solution. That's the only function in the whole wide world whose derivative is 3x squared plus 1 that happens to also pass through the point 2, -3. That's pretty darn particular, right? So particular, my wife would approve. Right? Ooh, felt that. Okay. So this involved nothing other than what we've already been doing, anti-differentiating both sides. The only difference is the way it's presented. You have to understand that, oh, we're doing the same thing. We're just doing it in a slightly different context. Okay. Now, that is by far one of the easier differential equations we'll be solving. Yeah, they get more interesting. And then really, when you go on to higher level calculus, you take Cal 1, Cal 2, sometimes there's even a Cal 3. But then the capstone calculus course is called DiffEQ, which is short for differential equations. And what you do is you put all your calculus knowledge together to solve differential equations. And some of them require some crazy substitutions called Laplace transformations. And it's really exciting stuff, because the jumping off point for the world for the study of things that change is not Cal 1. It's really differential equations. But you need all of that information that you learned through Cal 1 and Cal 2 to understand differential equations, okay? Because everything in the world is changing. We observe the change, we try to extrapolate backwards. That's how those kinematic equations came into existence. Let's look at those real quick. The kinematics.
Oh, geez, don't bring me back.
Acceleration of a falling object on or near the surface of the Earth at any time t is given by, in feet and seconds, is given as -32 feet per second squared, right? Or -9.8 or -10 if you're on the AP exam, because you can work more problems without a calculator. But about 9.8 meters is about 32 feet, okay? What? In here we use feet. In science, you use meters, right? We use hands and feet in here. We don't let any part go to waste. Now, this is an observable, measurable, not theoretical, but empirical. What did you, observational, experimental. There you go. This is an observational, experimental, empirical value. We can observe this. This is a differential equation. How do we know this is a differential equation? Because it's equal also to v prime of t. Let's find the antiderivative of both sides. What's the antiderivative of v prime? V. And then what's the antiderivative of -32? -32 x, or in this case t, right? Plus a constant. Now here's what I'm going to do. I'm going to say let this constant equal v sub o, or v sub I, whatever you use in physics. This then becomes -32 t plus v sub o. V sub o is just what's going to turn out to be initial velocity. Okay. So we have now a velocity, an instantaneous velocity equation for something on or near the surface of the Earth. But wait, this is also a differential equation, because this is equal to what? X prime of t. So let's take the antiderivative of both sides. Let's use y prime, because it's falling object, right? So vertical. Or do y'all use h? I don't know what you use. Do you h? Okay, I don't care. It is a falling object. So height. Rate of change of the height. So what would be the antiderivative of little h prime? Little h, right? And now what's the antiderivative with respect to t of -32t? Well, -32, you go along for the ride, get in the back of the truck, leave a little space. We have t to the first, so what do we do first? We add 1 to get the new exponent, and then we multiply by the reciprocal to neutralize the acid, right? We eat the enchilada, and then we eat the antacid right after it. Reciprocal of the enchilada, right? Next time you're eating enchiladas, ask the waiter, excuse me, do you have any reciprocal of enchiladas back there? And see what they said. I had too many enchiladas. I need some reciprocal enchiladas. Plus, what is the antiderivative of v sub o, which is a constant? V sub o times or t, right? If it's a constant and you're anti-differentiating, you just add a t. And then plus another constant. Now, I'm going to say let c equal h sub o. This becomes then negative 32, or I'll bring the 1/2 in front. I'm going to call this negative 1/2 times 32. Instead of calling it negative 16, t squared plus v sub o t plus h sub o. And now little g is nothing more than 32, right? Feet per second squared. It's also about 9.8 meters per second squared. So if I then substitute that, which I could have just worked with g the whole time, it's negative 1/2 g t squared plus v sub o t plus h sub o, where v sub o is the initial velocity and h sub o is the initial height, and g is the acceleration due to gravity. Yeah. So those kinematic equations came into existence in the reverse order that we learned them. The world starts with differential equations. So knowing how to solve a differential equation is the key crux in any calculus class. But like anything else, you know, we kind of learn it in reverse because we need to learn the parts before we learn the big whole, right? The big complete whole, right? Big hole, like black, like it needs a Snickers. Have you seen us do a commercial? Earth, it looks like you need a Snickers. It was like at last year's Super Bowl. Yeah, you're not new and you're hungry, Earth. Here, let's drop a giant Snickers into the hole. Yeah, I wonder what this year's commercials are going to be about. All right. Go, Joe Burrow. All right. How do you feel so far? Do we have time for one more? We do. Let's do one more. Let's do one more. Let's do one more. Let's do example 4. We could do it, guys. We could do it. dy dx equals e to the x plus 20 times that quantity, and y of 0 equals -2. Find the particular solutions. Well, here's your initial condition, right? That guy's waiting in the wings. That's an ordered pair on the function y. That's an ordered pair 0, -2. I like to see it as an ordered pair, so I always rewrite it like that. Now, do I need to do any rewriting on the right-hand side? The e to the x looks good, but what the heck is the antiderivative of 1 plus x squared to the -1?
That's actually tangent inverse.
Ah, very good. The way it's written right there, I can't really do much with it, even after I find advanced techniques. But if I say that that's the same as 1 over 1 plus x squared, now I'm like, what's up, derivative of arctangent of x? And see why it's important to know your derivatives going forward? Because you got to be able to recognize them going backwards. You don't want them to be slapping you in the face and you being like, stop it, stop it. They're trying to get your attention. You'll be saying like, thank you instead. So the left side becomes y equals, and here we go. What's the antiderivative of e to the x? E to the x, boom. Plus 20 goes along for the ride. What's the antiderivative of 1 over 1 plus x squared? Inverse tangent. I'm a fan of writing the word arc of x. Plus c. Plus c. This is the general solution. Now we find the particular solution. So below there, we'll say at the point 0, -2, colon. We plug in a -2 for y, -2 equals and a 0 for x. E to the 0 plus 20 arctangent of 0. And now I simplify. E to the 0 is 1. And what is arctangent of 0? Tangent of what angle is 0? Remember the graph of arctangent looks like this. No. Look, here's the graph of arctangent right here. It passes through the point 0, 0. Yes, thank you. Right? So arctangent of 0 is 0. And so this becomes -2. Oh, plus c. Don't forget your plus c. Yeah, sorry. I was like, where'd c go? So we get a 1 plus c. So c is equal to -3. And now we write it in the very end. We say so, and we plug it way back in up here to the general solution. So y equals e to the x plus 20 arctangent of x -3. Oh, perfect timing. Love those antiderivatives. Love them, love them, love them. It's a lot of fun. Trust me, when we get to 4.4, you'll believe me. You'll be a believer. Have a good lunch. Have a good day.